Well, I appreciate the opportunity to participate in the symposium here. I'm very sorry that I'm doing so remotely. In my enthusiasm for the symposium, I confess I got a little overly optimistic about travel, or should I say irresponsible about travel. But appreciate the ability to present remotely. So what I wanted to do in the next few minutes is introduce you or remind you of a mechanical phase transition controlled by primarily strain, and how this provides a very useful theoretical framework, and actually even increasingly quantitative theoretical approach, I would say, to understand especially nonlinear rheology, but more generally rheology, and a number of elastic effects of interest I'll get to toward the end in extracellular matrices. So these are, so our tissues depend for mechanical stability on matrices such as collagen here. For some reason, I have no mouse, but that's okay. So on the left, you see a beautiful image of collagen from my colleagues back then in Amsterdam, now in Delft, Gijsje Koenderink's group. So this is collagen type 1. These form thick filamentous proteins, biopolymers, fibers, you could say. And an important thing to start realizing when looking at these kinds of networks is the diameter of these collagen type 1 fibers is already of order 100 nanometers. So it's pretty far from the molecular scale you might be thinking of in other polymer systems. And so this begins to point to one important characteristic that I need to emphasize for our intuition going forward. And that is that you should think of these as essentially fully athermal systems. If you like, they're sort of mesoscopic elastic fibers, rods. And that has some interesting consequences. Among other things, one of the important aspects in trying to understand these systems theoretically is their deformation or response to external stress winds up being very heterogeneous, very non-uniform. Of course, this is referred to as non-affine deformation or strain in these systems. And unlike flexible polymers, that non-affinity is not just resulting in some quantitative change in something like a modulus, but it is essentially everything. It is the dominant effect. And so we'll see this as we move along. So these systems are highly nonlinear. This is one reason why I would like to look at what happens as a function of strain ultimately. And just to illustrate that nonlinearity, I like this classic work going back to Feng in the 1960s, showing the nonlinear mechanics of collagenous tissues. And what you see here is something on the left, which is very far from a Hookean response. You get a strongly nonlinear, specifically stiffening response for these tissues. This is subject to extensional strain. The experiments I'll be showing you later will be shear, which is what's used mostly for the collagen network work. But Feng already plotted these data a little different way. He plotted the derivative of the force versus extension as a function of force. So a tangent modulus, essentially, the derivative of stress with strain. And this is something I will be referring to throughout as the modulus. It's a nonlinear stiffness, you could say. And that's shown on the right here. And what you see is, well, don't be fooled by the straight line. This is not linear. Linear in this case would have been a horizontal line. So what you actually see instead is a very strong increase in this stiffness, this nonlinear stiffness, of approximately 2 orders of magnitude. So this is typical of tissue. And you actually know this by just pulling on something like your earlobe, that it's not very Hookean. You see a strongly nonlinear response and specifically stiffening. So this is generic. Actually, it's generic in a number of biological biopolymer systems, not just collagen or even extracellular matrices. Anyway, this work has been very influential in early understanding of tissue mechanics, and has been reproduced many, many times over the years. I'll be talking later about somewhat simplified, constituted collagen networks primarily to try and understand the main ingredient, so to speak. Okay, so how can we understand this sort of thing? Well, let me begin with something that I don't need to introduce in this audience. This was already discussed somewhat yesterday, but I just want to remind you of this elegant argument going back to the 1860s by Maxwell, leading to this isostatic criterion for the stability of a network connected with at least Hookean springs, of a local coordination number equal to twice the number of dimensions we're in, 4 in 3D, sorry, 4 in 2D, 6 in 3D. And this isostatic condition tells us the connectivity above which I have a linearly stable structure and below which I have a floppy structure, of course. So what can this tell us about these sorts of networks I'm talking about here? Well, collagen is shown on the left here. Intracellular networks are somewhat similar, shown on the right. Well, at first sight, this sort of argument doesn't tell us very much because generically, the physiological coordination number that's relevant for these networks winds up being actually substantially below even 4, let alone 6, which would be the relevant coordination number for 3 dimensions. So these should be in the floppy phase, at least with respect to central force interactions. And this is a useful starting point, but it doesn't explain the stability of these networks, of course. So one of the things that's obviously missing in this argument is suggested by these zoomed in images I'm showing on the left of coordination number 3 and coordination number 4 junctions. You can also start to imagine that these fibers are possibly resisting bending, and they do. I mean, for collagen type 1 networks, I've already indicated you should think of these as athermal fibers. If you were to talk about what's called the thermal persistence length for these systems, it would be meters. They're essentially, as I said, athermal. So they're certainly resisting bending. However, in an interesting way, that bending response is still much weaker than, of course, the corresponding stretching response. Okay, so let's think about the implications for this. So I'm plotting here the rigid phase on the right of this transition point, the isostatic point, floppy on the left, but I want to strain these systems. And this can be bulk strain, it could be shear strain, could be uniaxial strain. Shear strain is, I would say, the important one for comparing with most experiments. But why would that result in stabilizing systems? That's what I'm going to argue. Well, this idea has been around for some time, going back even to some of the flexible polymer literature about stress stabilized systems. It also relates a little bit to engineering notions of tensegrity, et cetera. But we actually know this from everyday experience. This structure here, spider web, you could say would have been a floppy system if it had not been stressed at the boundaries, or if you like, stretched out to these boundaries as shown. Of course, that's not the way the spider forms this network, but that's one way to look at the resulting structure mechanically. And before you start worrying about the local fourfold coordination in this seemingly two-dimensional structure, That's not really, I would argue, relevant for the stability of this system. You could, I assure you, you could go in and snip a significant fraction of these bonds, and you might make the spider unhappy, destroying its nice work here. But I assure you, you can still have a stable structure. You would probably have to stretch it a little bit more to reach this stable point. And so that already starts to illustrate that this boundary that I'm arguing for between floppy and rigid shifts to higher strains at lower connectivities as you go away from the isostatic point. And again, let me just remind you that physiologically, everything is happening far below that isostatic point for the networks I'm talking about. Once I add bending, of course, to describe those systems. But I'm still focusing on the fundamentals here of the stretching response, if you like. So just to illustrate this a little bit more, I want to show a cartoon. I think it's very instructive. So what I'm going to do is I'm going to create a sort of spider web, but I'm going to do it from a diluted triangular network. So I'll start with a random diluted spring network on a triangular lattice. And I'm going to subject it to bulk strain, so a little bit like what I was arguing for that spider web, stretching it at the boundaries. And so if the strain is uniform, then what you should see is basically the image should just uniformly expand, right? But what I'm going to do in order to focus on the non-affine deformations that I already mentioned are so important, I'm going to change the field of view so that the full network is always in the same, covering the same region. So what that means is any motion that you see in this cartoon will actually be the non-affine deformations, okay? So the absence of motion just corresponds to a uniformly expanding system with lower magnification. Okay, so let me run the movie. You can see a little bit of motion, not too much. And now a little bit more motion and quite a bit right before I stopped. Now, hopefully, you also noticed that not only was there a lot of motion right before I stopped, but maybe you can imagine that that motion was characterized by larger correlated regions moving. And that is indeed the case. So I want you to start thinking about that motion you were just looking at, which again is the non-affine deformation, as something analogous to critical fluctuations ultimately, for which there's also a corresponding diverging correlation length. So those are indeed useful ways to look at this, and I would say even valid ways to look at this. But back to the mechanics, everything I just showed you, all those deformed states that I was going through as I was, again, stretching this system uniformly at the boundaries, they're all linearly unstable. The original network was for a 2D network below that isostatic point, and the network remained in the floppy region that I'm showing here. Oh, now my mouse seems to have shown up again. I hope you can see that as well. So I was basically following this floppy region here. Okay, so actually, I also can back the movie up slightly. Hopefully you can see this. And again, hopefully you can realize, you can see that you're getting large correlated regions that are moving in these non-affine deformations. Okay, now if I strain any further, I claim that I will cross the boundary to a rigid state, and that is indeed the case. I get some more rearrangements, notice right after the transition. You hopefully can start to make out some red lines showing up here. These are tension-bearing lines. So I've got actually, you could say, a propagation of a force network from one side of the sample to the other. And the result is a very drunken spider web, if you like, highly stretched, but you know, at least the idea is a system stabilized by strain. So I've crossed this boundary. Now, one of our interests early on was to understand the nature of this transition. That a transition exists maybe isn't surprising based on what I've just described, but I want to argue that it's actually a line of critical points. It's a second order like transition as a function of strain. And the beauty of that, from just the point of view of studying critical phenomena, is strain is a much easier variable to control in these networks than, let's say, connectivity. I should also point out, for people thinking about jamming systems, connectivity is not a variable for us, if you like. It's a frozen architectural aspect of these networks. So these networks are permanently cross-linked with a fixed connectivity. Okay, now, the result of what I just described, though, would have been a transition from a fully floppy, zero rigidity, zero modulus state to a finite modulus state. But what's missing in that picture for collagen networks especially is bending resistance. And so I'm going to add bending resistance to this diagram by coming out of the plane in the third dimension. And what I've just described as a transition only occurs in the plane at zero bending rigidity, and I'm describing bending rigidity by kappa. There are other stabilizing effects you can consider as well, by the way, and we do. One interesting one is temperature. I've argued that the system so far is athermal, but of course, entropic elasticity can be thought of as stabilizing a mechanically floppy system by thermal fluctuations. Something similar happens here. Interestingly, with anomalous temperature dependence, but that's a separate story. So with bending resistance, what happens is this floppy phase goes away. It's stable, it just happens to have a low modulus. So in these experiments I'm showing on the right, collagen, importantly, by the way, I also want to point out that this is a collagen network at 1 milligram per milliliter. So that is a 1/10% volume fraction, approximately. And so what you have is a very soft modulus, just a few pascals, a couple pascals as it is, on the extreme left. Notice the log-log scales and highly compressed log-log scales. As you strain the system and go through what would be the transition shown as the red line on the left, that's indicated by the red X on the right, what happens is that the mechanical resistance, the shear modulus, goes up by about 2 orders of magnitude and would continue further as one goes into a more stretch-dominated regime, except that this particular sample failed, likely due to delamination of the rheometer plates. Now, I mentioned that the volume fraction is a 1/10% volume fraction, 10 to the minus 3. It's not a coincidence that there's about 3 orders of magnitude of stiffening here. And that's because the naive dependence on volume fraction for a fully stretching regime would just be that the modulus would be proportional to concentration. For the bend regime, however, it should go like the concentration squared. And a simple way to see that is if you take a network of fibers and you simply, in the same network, and you increase their diameter by a factor of 2, you increase their cross-sectional area by a factor of 2, let me do that. Then the volume fraction would go up by a factor of 2, the stretching modulus would go up by a factor of 2, but the bending modulus would go up by a factor of 4. And so that basically begins to suggest that the relative importance of bending to stretching is proportional to volume fraction. That, on the one hand, means that bending is naturally a small parameter in these systems. It also tells us something about the range of stiffening available for these systems. Okay, so the real systems are not in the plane I showed you going through the transition. They're slightly removed out of the plane into the half space in front of the plane, but close enough that as we move near what would have been a thermodynamic transition, I still see a strong signature, in this case, rapid increase in the modulus. If I could make an analogy with ferromagnetism, it would be something like studying something like iron as a function of temperature, but at finite field. I would never go through a transition, but if the field is small, I would see a very strong increase in magnetization as I move near the transition. Okay, so that's a useful way to think about it, except I should also warn you, you should not think of the stiffness as an order parameter. So that is something I need to warn you. Okay, so how can this start to tell us about collagen networks more quantitatively? Well, so on the left, I'm showing the experiments above and a result of various simulations you can do in 2D and 3D. I'm just sketching some structures to illustrate the kind of simulations you might do. And so one thing to notice is if I went back to Maxwell's original picture of Hookean springs and simply strained the system, I would have gone from a floppy state with 0 modulus, so that would be off at minus infinity here on the log-log scale to the left of my red dashed line. And on the other hand, if I strain the system past that critical strain where the stiffness develops, I would follow this dashed line up to finite values of the modulus. And it turns out that actually grows as a power law with an exponent f, power law of strain minus the critical strain, certainly suggestive of critical phenomena. And what you find from these sorts of simulations is a exponent of between 0.7 and 0.8. Now, it's not a nice ratio. It's not a nice integer. That's already beginning to suggest that maybe this is not a mean field exponent, and it's not. The mean field exponent for this would have been 1. So that's an interesting aspect to start hinting at. And so let me just briefly sketch for you how one way to start thinking about this kind of a thing, motivated by essentially Kadanoff's approach to well, on the one hand, real space renormalization, on the other hand, start to derive what you might expect for the scaling function describing, in this case, the elastic energy. Again, this is an athermal system. So I want to think about the elastic energy as a function of strain and bending resistance. So that's gamma and kappa here. And I'll introduce a reduced temperature-like variable for the transition, which will be the difference in strain from gamma C, the critical strain. It can be both positive and negative. And so if I imagine that elastic energy as a function of those two parameters, T and kappa now, near the transition, those are small. Those quantities are small by definition. And I also wind up having a large correlation length. So if I rescale my system, it should look the same, and I'll rescale by a factor of L, which is what's shown here. I should see qualitatively the same behavior, but with a corresponding smaller, by a factor of L, correlation length, i.e., I should be farther from the critical point. And basically, pushing those ideas through, you wind up getting a simple but highly restricted mathematical form of a homogeneous function for this elastic energy. And you can start taking derivatives of that elastic energy to get things like stress or strain. Sorry, to get stress or stiffness by taking derivatives with respect to strain. So the stress would be one derivative with respect to strain. The stiffness, this K that I've been talking about, the derivative of stress with strain, would be two derivatives of the energy with respect to strain. That would be somewhat analogous to taking two derivatives of a free energy with respect to temperature in a thermodynamic phase transition, corresponding to a heat capacity. So as I said, one should not think of this K as an order parameter itself, which you can do for a linear modulus, let's say, in the original Maxwell picture. But you should think of this K as something a little bit more like a heat capacity. Now that's important because what happens in detail is that this K shows a discontinuity at the transition, which a number of people have pointed out over the years. And that has nothing to do with the order of the transition. So don't think of discontinuity of that in terms of a first order transition. Now, what you get from taking this derivative and then rescaling specifically to by a factor that that corresponds to the correlation length is you get a simple scaling form for K, where it should depend on that power law of gamma minus gamma C that I mentioned before, times some function of a ratio of a scaling variable, which would be kappa divided by gamma minus gamma c to some other power, phi. You also begin to get scaling relationships between exponents. That's very important. And those familiar with critical phenomena in a little more detail will recognize one of these scaling relations, the first one I'm showing here for F, in terms of the correlation length exponent nu, as a hyperscaling relation. And we were particularly interested in looking at this in work with former student Jordan Shivers a couple of years ago, because this can give us some insights into mean field, non-mean field behavior, possibly even upper critical dimension, so-called. And the point is, we see non-trivial hyperscaling in dimensions 2 and 3. And so the system apparently has a upper critical dimension of higher than 3. Okay, now, what I want to do, though, is go back to this relationship I've shown here, the scaling function for stiffness, and I'll show it again here on the lower left, for mechanical systems, and remind you of an analogous thing done for ferromagnetism. Again, I'm not saying K is an order parameter. You can do this for quantities other than the order parameter, of course, but you get scaling relationships you get a scaling function which is somewhat similar. And of course, what you find in magnetic systems is that you can collapse all data, at least near the transition, of magnetization as a function of field and temperature onto one curve with two branches, one corresponding to the paramagnetic, one corresponding to the paramagnetic or ordered phase. For us, the ordered phase is at high strain, corresponding to, if you like, low temperature in the ferromagnetic system. So does this work? Does the scaling relation work? Well, so we plot K divided by this factor of gamma minus gamma c to the F. Again, apologies, I seem not to have a mouse. And plot that versus stiffness divided by this other factor of delta gamma, if you like, or reduced temperature. And sure enough, the data do collapse. Certainly strongly suggestive that at least our simulations are showing second order like behavior. You can also get estimates for these critical exponents. This happens not to be the very best way to do it, but it can be done. And importantly, this also works for experiments. So for the experimental data, but just before showing you that, let me remind you, I argued before that kappa should correspond to the volume fraction of networks. So what we'll do is we'll divide stiffness by concentration to effectively account for just the overall concentration, the overall amount of polymer available. But then our scaling variable that appears in the scaling function W, in honor of Whittam, is going to be concentration divided by distance from the critical point in strain to a power phi. And that gives, in fact, pretty good collapse of the data. In fact, arguably, this collapse is well, I mean, it's starting to approach the kind of collapse you get for ferromagnetism. So certainly begins to show us that again, the nonlinear, and this is coming from the nonlinear strain stiffening response that I showed you before for collagen. I showed you one data set before. This is actually for collagen spanning about an order of magnitude in concentration. So quite a range there. It's about what the limits of what one can do experimentally. There are important limitations. The other thing, too, is that this relation down below begins to give us an actual functional form for the mechanics, if you like, an equation of state. And that was the dashed line that I showed you before that went through experimental data. I neglected to mention that before. So you can actually get a good quantitative agreement between this theory and experiment. So let me turn in the last few minutes to some of the mechanical signatures of this phase transition, consequences of this phase transition. Now, one of these people have looked at quite a bit over the years has to do with the Poisson ratio. So let me just remind you, Poisson ratio tells you about the relationship between transverse strain when a sample is subject to a uniaxial, let's say, extension. If I strain uniaxially by 1%, for a volume preserving system, I would contract correspondingly by 0.5% in each of the two transverse directions in 3 dimensions. That corresponds to a Poisson ratio of 0.5. It's actually an upper bound on that ratio as well, because you do not expect samples to reduce their volume under traction.
Greg, you have 5 minutes for questions.
Okay.
Yep, 5 minutes.
So 5 more minutes, then questions, right? Yeah. Okay. Yes. So this is actually something which has been shown to be, if you like, violated many times by these extracellular matrices. I should point out this upper bound is for a linear isotropic elastic material. So, you know, there are limitations to this. But I mentioned before that that upper bound corresponds to an well, if you go above that, that would correspond to an unphysical situation, unexpected situation, I should say, where a system would reduce its volume under traction, or it would have something like a negative compressibility. And that's basically what was reported in these experiments here. I happen to like this plot a little bit better because it nicely shows the deviation. The dashed line corresponds to the Poisson ratio of 0.5, and a deviation below that corresponds to having a Poisson ratio in excess of 0.5. But it is a nonlinear effect, and so it's not violating that dynamic bound, but it is at least a surprising effect that surprised many people when they started doing these experiments. You see very dramatic volume reduction of 80% in this case at strains of order 5%. And even already strong violations at strains of order 1 to 2%. And so what Jordan has showed a couple years ago is that this sort of signature of a peak in what is now a differential form of the Poisson ratio, derivative of transverse strain with respect to longitudinal, it actually peaks to values of order 10, consistent with experiments. And it does so in a way which coincides with those non-affine fluctuations I was telling you about. In fact, you can show that this peak in the Poisson ratio is fully tracking that phase boundary I indicated before. And that's nicely illustrated by this heat map down here, where the peak in the Poisson ratio, look at this nonlinear Poisson ratio, follows the phase boundary, and again coincides with the inset here of the strength of the non-affine fluctuations. So these non-affine fluctuations are growing also in correlation length at the transition, and that's happening at this onset of this elastic anomaly. So another interesting thing to think about with these non-affine fluctuations is there are rearrangements that are occurring in a background fluid. And so there should be dissipation associated with that. And that leads us to the last thing I'll talk about in any detail, which is critical slowing down. So I'll do this quickly, but basically as you cross that phase boundary, you might expect some signatures in the dynamics, and indeed you do. This is showing the relaxation modulus. For the following kind of protocol, strain the system to some initial strain gamma naught, let it relax, and then give it an incremental step strain at time t equals 0 by an amount delta gamma, and then ask how the stress relaxes over time to a new equilibrium. And if you're in the fluid phase or the floppy phase, that stress would relax to 0, corresponding to the blue curves on the left. And if you're in the solid phase, in the rigid phase, it would relax to a finite value, a residual stress, and finite modulus, corresponding to the red curves. But notice what's happening as you get near the critical point. That's the gray curves. The corresponding relaxation times grow. They literally diverge, subject to, of course, finite size limitations. Again, coincident with those non-affine fluctuations. And as as this relaxation time grows, you won't be surprised to learn that viscosity, specifically the intrinsic viscosity minus the fluid viscosity, of course, peaks also coincident with those relaxation times. That's again shown for a variety of samples with different connectivities and corresponding critical strains in both 2D and 3D by, again, sort of heat maps showing that that divergence of the viscosity is occurring along that phase boundary. And importantly, this works for packings of particles. This is something that people have seen before, but this is for fiber systems, which have not been studied this way. And it also works with and without bending resistance, as I'm indicated. Bending rigidity does take you away from the critical point, so it does suppress the peak in a way consistent with what you might expect. But interestingly, all those systems fully collapse so that the viscosity signature perfectly tracks the non-affine fluctuations. And the reason we were excited by this is experimentally identifying those non-affine fluctuations has been a big challenge. Visualizing them has not been very successful. I mean, people certainly tried and done nice work, but to really get these critical fluctuations has not really been successful, it's fair to say. And so to have a rheological readout, so to speak, on that non-affinity is one of the things we were interested in. I don't have time to go through something else, but I'll just indicate looking at local incompressibility of networks is very interesting. And this, again, affects the non-affine fluctuations I was talking about, because some of those fluctuations will be compressive in character, some will be volume preserving in character. And interestingly, there's a stiffening of networks that's associated, we believe, with the suppression of the volume non-preserving parts of the non-affine fluctuations, as happens when you put in hyaluronic acid, an important extracellular component which does suppress local volume fluctuations. So I'll end there. There's other stuff you can do. I've left out a lot of the more technical bits on the theoretical side, including very recent developments of effective medium theories or mean field theories for the transition 2D and 3D. Importantly, these effective medium theories are not lattice-based, so we've freed ourselves, if you like, from the lattice, which has been the subject of most prior effective medium theories. We also begin to understand where the non-mean field effects are coming from. And it has to do with interesting effects of disorder in a way which appears to be much stronger than corresponding jamming systems, which is an interesting thing to look at. I mentioned briefly thermal effects. This is also interesting, but I'll end there. Thank you.